All right, let's go ahead and look at section 2.5, where we're going to talk about finding all the zeros of polynomial functions. So far we've learned how to find the rational with rational roots theorem. We found real ones. Now, really the only ones we're going to try to find in this section are the complex, things in the form a plus bi. So we're going to find all the roots. So we're going to hear one of the major theorems in math today, and that is the fundamental theorem of algebra. The fundamental theorem of algebra says this. It says given any polynomial function, so obviously these things that we've been working on for the last few sections, given any polynomial function, there exists at least one root in the complex number system. Now you might think this is a worse theorem than the one that we had in section 4, which said that if you have a degree n, then you have at most n real roots. But it's actually a much more powerful theorem. Even though this is the official theorem, where it's basically saying, all right, if you have a polynomial function, f of x, let's say it's x cubed minus 5x minus 2. That means there is at least one complex number solution. But the nice thing is, if we find that one complex number solution, we can divide out, and then we'd have a second degree equation. And then you could use this theorem again and say, well, this one has to have at least one as well. And then you could go to a first degree, and it has to have at least one as well. So the big idea is you can actually break this into an even more powerful theorem. And that's what we sometimes call the corollary or the consequence of the fundamental theorem of algebra. The consequent fundamental theorem of algebra says this. It says given an n degree polynomial function, so I have some polynomial function with the highest degree being n, there exists exactly n number of zeros in the complex number system. So if you give me a degree polynomial, then I can find that many roots in the complex number system. Now, some of them are not very easy to find, but let's say, for example, let's say I have the polynomial function 5x squared cubed minus 4x plus 2, then I know there are exactly 3 zeros for this polynomial function in the complex numbers. That means some might be complex, some might not be. There's some mix, but there is exactly 3 of them that I'm looking for. So whatever that power is, that's the number of zeros we're actually going to be looking for. So now we're going to start looking at complex roots. We have one theorem that can kind of help us with that, and that's called the complex conjugate pairs theorem. And this theorem just states that if a plus bi is a root or a zero of f of x, so if it's one of our zeros that we're looking for in our degrees, then we say so is a minus bi. The idea of a conjugate in algebra is basically you have the same two numbers separated by a different sign. So, for example, if I have a polynomial and 3 plus 2i is a root, then so is 3 minus 2i. These would both have to be roots. If negative 7i is a root, then positive 7i is a root, because this is like 0 minus, so 0 plus. Same idea. So, if you have one of these imaginary roots, you have the other as well. So we can actually use these to find some different polynomials. Now, a couple things about imaginary numbers that we should probably review. Remember, in general, if you have the square root of negative 1, it is I. That's why we're getting these imaginary numbers, because they're not real numbers that we know. And that's really the only number in existence that if I square that number, I get negative 1. So it's the only number you can square and get a negative number. And this relationship will actually help us a lot with a lot of the problems we're doing today. So let's look at our first example. It says, find a degree 3 polynomial with zeros of 1 and 2i. Well, by the fundamental theorem of algebra's consequence, if I have degree 3 polynomial, I need to know 3 of the zeros. I know 1, I know 2i, so I'm really just missing one of them. But if you recall, we said from the complex conjugates theorem, if 2i is a 0, then negative 2i is a 0 as well. So those are my zeros. But in this problem, it says I want to know what's a polynomial function. So I want some answer at the end. This says f of x equals x to the third and a bunch of other stuff in this polynomial. That's what I'm looking for. So the way we typically do this is, since we have these 3 zeros, we will start our polynomial function f of x. I will turn each of those into a factor. Remember, we said if 1 is a 0, x minus 1 is a factor. So if 2i is a 0, x minus 2i is a 0. And if negative 2i is a 0, x plus 2i is a 0. So the only tricky part about this is we now have a lot of algebra to do. So we just have to FOIL these 3 things together. Now what I would do is I always take the complex conjugate pairs, because if you have 2 complex conjugate pairs like we do here, these will always FOIL the same way. It FOILs as an x, it FOILs, as an x squared, it FOILs as a minus, and it FOILs as the last number squared, which is 2i squared. So, you square the first, you square the second, and there's a difference by a minus sign. Now, it will actually help save us a lot of time when we're doing some of this FOILing. So, I'm going to leave the x minus 1 alone, but if I simplify this, I get x squared. So I'm trying to figure out what is 2i squared. So if I go over here, 2i squared is 4i squared. But remember from above we said I squared is negative 1. So this is 4 times negative 1, which is negative 4. So this becomes x squared minus a negative 4. So this is x minus 1, and then x squared plus 4. So x squared plus 4, we've kind of put these 2 complex roots and made them into a real valued polynomial. So to finish up, all I really have to do is FOIL these 2 things together. So x times x is x cubed. X times 4 is 4x. Negative 1 times x squared is negative x squared. And negative 1 times 4 is negative 4. So my polynomial function is going to be x cubed minus x squared plus 4x minus 4. So that polynomial function that I have there is the one that has zeros of 1, 2i, and negative 2i. So if I were to plug in 1 or 2i or negative 2i, I would get 0. So definitely a lot of algebra you have to be careful of. Let's look at our last one here on this page. It says find a degree 4 polynomial with zeros 2 plus I and minus 5i. Same idea. If I want to find the other 2 zeros, I know one is going to have to be 2 minus I and one's going to have to be positive 5i. So in this case, they're all complex roots, which is okay. Because we said as long as you're a degree 4, you should have 4 zeros under the complex system, and we do. So if I want to write a polynomial for this, g of x, a little trickier because we got a little harder roots. We have x minus 2 plus I, always 2x minus the root, and then x minus 2 minus I, so those are our first 2, and then x minus 5i, and x plus 5i. So that's relatively simple. It's the algebra and putting these things together. So I would FOIL these 2 together using the idea that they are differences of squares, and the same thing here. So this one down here, this is going to become x squared minus 5i squared. So that works with just like the one above. Now this one you can do lots of ways. I'm not sure there's really a good way, but this one's not really, see how this one's plus and this one's minus? You really don't have that here unless you rework it a little bit, but we can certainly do that, because if I rewrite this as x minus 2 plus I and x minus 2 minus I, well, I did that backwards, but I'm basically distributing the negative sign. So I did this one here and I did this one here, but same idea. So when you do your conjugate, you have to group the first two and then the last I. So when you FOIL this, it's going to be x minus 2 squared minus I squared. And then x squared minus 5I squared. And again, this algebra is very hard, very tricky. So if I take x minus 2 squared, I'm going to get x squared minus 4x plus 4. And if you're unfamiliar, that's just because I'm taking x minus 2 times x minus 2. That's how I got that. But then I have minus I squared. Well, I squared is negative 1, so this becomes plus 1. And over here we get x squared minus 5I squared, just like above, becomes negative 25, so plus 25. So if I simplify it, I get x squared minus 4x plus 5 times x squared plus 25. So from there, all I have to do is FOIL that together to get our final polynomial. So what I might do is, what I'd probably do is start with the one on the right, multiply the x squared to everything, and then multiply the 25 to everything. So x squared times x squared is x to the fourth. X squared times minus 4x is minus 4x to the third. X squared times 5 is 5x squared. And then with the 25, 25 times x squared is 25x squared. 25 times negative 4 is minus 100x. And 25 times 5 is plus 125. So our final polynomial is going to be x to the fourth minus 4x cubed plus 30x squared minus 100x plus 125. So that's an extremely difficult one, but it will have the zeros that we mentioned above. So the more fundamental problem we'll see is when we actually are trying to find the zeros. Okay, let's look at an example of one. So we have a function, and we have the function x cubed plus 6x plus 20. So if you look at this, the degree of this function, the degree is obviously 3. It's the highest power in the polynomial. So by a consequence of the fundamental theorem of algebra, like we talked about earlier, that this f of x has precisely 3 zeros in the complex number set, because the degree is 3, so there's 3 zeros. So our goal is to find 3 zeros. And of those three zeros, at most 3 of them are real. Okay? So we are really looking for 3 real zeros. But there could be less. And I'm pretty sure in this case there will be less. Okay? So what we'll do here is we will look for some different rational roots. So the first thing I'll do is I'll look for factors of p and q. P is the factors of the constant. So I have this written backwards. So this is our p. P is 20, and q is the leading coefficient, which is 1. So the factors of p, so what multiplies to give you 20 could be 1 and 20. So I put plus or minus 1 and 20. I put plus or minus 2 and 10. What else multiplies to 20 would be 5 and 4. Now what multiplies to 1 is very simple. It's just plus or minus 1. So what we do is we take all the factors that are of the last number and all the factors of the first number, and we divide them. So if I take 120 and all those and divide it by just 1, then my list of possible rational zeros is just going to be plus or minus 1, plus or minus 20, plus or minus 2, plus or minus 10, plus or minus 5, plus or minus 4. So if there are any real zeros, then they would have to be in this list. Okay? Now the question is, how do I know if any of these are real zeros? How do I know if any of them work? That is the goal. Okay? So we can look at the first one. We can say, is x equals 0 a factor? This is always a nice one to get rid of, and it's a no. If I plug in 0, I don't get 0, as you can see, because 0 plus 20 is not 0. Okay? So it's not. But that's always something we should look at because it makes our life a little easier. So what I want to know is, of this list of roots, are any of them zeros? Okay, are any of them zeros? So what I went ahead and go do, I am going to plug in all these numbers if you want. I'm not going to do that. What I'm going to do is I'm going to graph this function. So when I graph it, I'm just going to kind of sketch it here. So the graph looks something like this. So it only crosses one spot. So one of the zeros they have, because I know f of 0, or f of negative 2 equals 0. Now how do I know that? I know that because when I looked at my graph, it crossed at negative 2. So one of my zeros, I'm looking for 3 zeros, remember, one of them has to be negative 2. So I have to find 2 other zeros. Now the graph does not cross any other places on the graph. It only crosses that one place. So what we have to do now is we have to use synthetic division to find out what the other 2 are. And this is where we're going to use our quadratic formula, our synthetic division, all the tools we've learned in this chapter so far. So right now, we know one of the zeros, right? So we'll list all the zeros. One of them we know is negative 2 because it crossed the axis at negative 2. We have to look for the other ones. All right, so what I'm going to do is I am going to divide out the one root I know. The one root I know is negative 2. So if I divide that out into my polynomial, which if you recall was x cubed plus 6x plus 20. So my numbers I'll put up there are 1 for the x cubed, 0 for the x squared, 6 for the x, and 20 for the constant. Just make sure we got that right. 1, 0, 6, 20. So we're going to go ahead and synthetically divide that. We'll bring down the 1. Negative 2 times 1 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is positive 4. 6 plus 4 is 10. Negative 2 times 10 is negative 20. So we're left with a remainder of 0, which makes sense because if you remember, our polynomial has a factor at negative, or a 0 at negative 2, so when you divide it out, you should get a remainder of 0. So right now, our remaining polynomial here, we started with a cube, we divided once, so this is going to be x squared minus 2x plus 10. It's a quadratic. So our two factors we have so far is we have x plus 2, because remember we had this negative 2 as a root, so we're going to put that as a factor. And we of course have x squared minus 2x plus 10. Now we've only found one of our 3 zeros. We have to find the other 2 zeros from this quadratic. But it's quite simple because now we'll just use our quadratic formula. So what we're going to try to do is we're going to try to figure out when is x squared minus 2x plus 10 equal to 0. So if you use quadratic formula, this is going to be negative b, so negative negative 2 is a positive 2, plus or minus the square root of negative 2 squared, minus 4 times a times c, all over 2a, which is 2 times 1. So if I work this out, this is 2 plus or minus, the stuff inside the root becomes 4 minus 40, which is negative 36 over 2. So this is 2 plus or minus, the square root of negative 36 is 6i divided by 2. We divide them both by 2, we get 1 plus or minus 3i. So my other two zeros, I found them now. They're complex, and that makes sense because if they weren't complex, they would cross the axis. We have 1 plus 3i, 1 minus 3i. So we just found three zeros. So no matter what your degree is, you can find them all. And if I want, I can actually write my polynomial in factored form. This would be kind of a bizarre factorization, but if you remember, our original polynomial was x cubed plus 6x plus 20. So I know that factors now is those three factors. X plus 2, of course. And now I found these complex roots, so I can factor this as x minus 1 plus 3i and x minus 1 minus 3i. So if you want to write it in factored form, once you know all these zeros, you just basically take x minus each of the zeros, and we are done. So really nothing new in this section. We're just kind of going through a lot of the different things we've learned this chapter and putting them all together. Okay, let's look at another one. This one actually, even though it looks a little more complicated, it's got a higher degree. So it's a higher degree, it has a degree 4, so we're looking for 4 zeros. This is actually a really easy problem. And all the work is going to be done by my calculator. So by the consequence of the fundamental theorem of algebra, this polynomial has 4 complex zeros because the degree is 4. And at most 4 of those are real. So it could be 4, it could be 2, it could be none. Now, is x equals 0 a factor in this case? In this case it is, because you notice they all have an x. And when they all have an x, then if I put a 0 for all the x's, obviously the function is going to be 0. So what I like to do is anytime you have this x, I want to factor it out, because I really don't want to deal with it. So if I factor it out, I get 3x to the third plus 20x squared minus 36x plus 16. So now if you look at this, I already know one of the zeros, right? So if I go down to the bottom here, it says list all the zeros. Well, cool, I already know one, I already know it's 0, because I had a factor. It said, what's the factorization? Well, I know one of the factors has to be x, because I just factored it out, just using GCF factoring. So now that I know one of them, I'm going to look at the polynomial inside. Now I'm only looking for 3 more zeros. And so we'll go through the same process we went through last time. We'll look at which zeros are possible. We'll plug them in the calculator, see which ones work, and we'll see if we need to find how many more we have to find. So remember, this is our p. Our p is our last number, and our q is our first number. So the factors of p, the factor of 16 is going to be 1 and 16, 2 and 8, and 4, and of course 4. The factors of 3 are just 1 and 3. So now I'm going to divide all the factors of p by all the factors of q. So if I do that, I'm going to take 1 through 4, and I'm going to divide them by 1, and then divide them by 3. So I have a lot of possibilities this time. I have 1, I have 16, and these are both plus and minus, 2, 8, 4, but then I'll divide them all by 3. So 1 over 3, 16 over 3, 2 over 3, 8 over 3, and 4 over 3. So all of these are possible. So what I'm going to do is I know if the graph is going to cross at any rational number on the graph, it's going to cross at one of these. But interestingly enough, when I look at the graph, I actually see 3 zeros where it crosses. This graph, now, what I would do is I highly suggest you put this into Desmos right now. Pause the video, put it into Desmos. Look where the graph crosses. I see that it crosses at these 3 intercepts, 2/3 and 0, 4 and 0, and 2 and 0. It crosses at all 3 of those intercepts. So I know that all 3 of those must be 0. And if you notice, those are all on my list. We got a 4 there, we got a 2/3. It says 0.67, but we know that's 2/3. And we also have a 2. So all of those were possible zeros, so it makes sense that those all could work out. So now I know more zeros. I actually know, down here, I actually know that 2/3 is a 0, I know 2 is a 0, and I know 4 is a 0. So I know all 4 zeros. So if you recall, We were just looking for 4 total, so we are actually done. So in this case, we do not need to synthetically divide because we've already found all the zeros. Now, if you have complex or irrational zeros, you will not get this lucky. In this case, this was a nice one. Everything worked out pretty nicely. Okay. So what I'll do now is I want to write the complete factorization, which is not tricky, but the one thing I want to be careful of, so I know x minus 2 is a factor and x minus 4 is a factor. Now, you can do this last one, the 2/3, a lot of ways. The easiest way is to just write the x minus 2/3. But I will claim to you, if I FOIL this out, I will not get the same number as I got way up at the top. Because you notice the first term is -3, and I have just x, 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 x. So what you want to do to make sure this is factored correctly, whatever the number is in front, in this case it was -3, you just want to tack that -3 right out front. So this would be the factorization. Now, quite honestly, we're more interested in these zeros and which ones are real and which ones are complex. But again, in this problem, most of them are just found by graphing it. Okay, let's look at our last one. We have x to the 4th minus 5x squared minus 36. So again, highest degree is 4. So we can have at most 4 real zeros. And has precisely 4 zeros in the complex number system. So we're going to have 4 zeros. We're not sure if they're real, complex, combination of the two. We'll have to find that out. And again, remember, this is all from the fundamental theorem of algebra. There are actually 3 major fundamental theorems of calculus, algebra, and arithmetic. This is one of the big ones. So first thing I'll do is I'll look for all the possible rational zeros of f of x. So these are my p's and this is my q. Now q in this case is just 1. That's nice. So really all I'm looking for is factors of 36. So the possible factors of 36 are 1 and 36, 2 and 18, 3 and 12, and 6 and 6. And again, this is just from the rational roots test. But we really like the rational roots that work out because we can just look at our calculator and see which ones work. So again, right now I would pause the video, put this into Desmos, type your x to the 4th minus 5x squared minus 36. So if you've done that, I see that this graph crosses 2 places. It crosses at 3, 0 and -3, 0. Only 2 places though. It does not give me the other 2. So I only know 2 zeros right now. I know 3 and I know -3. I'm missing 2 more. So we're not going to get as lucky as we did in the last one where we knew them all. We'll have to use our synthetic division. So we'll start with 3, and I'm going to divide 3 into my polynomial. Now remember how we write the polynomial. We write 1, I make a 0 because there's no x cubed, -5, a 0 because there's no x, and a -36. So I bring down the 1, 3 times 1 is 3, 0 plus 3 is 3, 3 times 3 is 9, -5 plus 9 is 4, 3 times 4 is 12, 0 plus 12 is 12, 3 times 12 is 36. And that should make sense because that was a 0, 3 was a 0, so it should give us a remainder of 0. Now interestingly in this case, I know another 0. So whatever numbers I have remaining, so I have this 1, 3, 4, and 12 remaining, I'm going to immediately divide the other one, the -3. So I bring down the 1, -3 times 1 is -3, I get 0. -3 times 0 is 0. 4 plus 0 is 4. -3 times 4 is 12, and I get another 0. So I divide both of them out, and I end up with 104. But what this really means is this is x squared plus 0x plus 4. So what I've just found is I've found a quadratic that will find my other 2 zeros. So I took both zeros I found simply just from the graphing, or the graph of it on the calculator, and now I end up with this. So to find the other 2 zeros, just like I did on the first problem, I'll take x squared plus 4 and set it equal to 0. Now again, remember, the degree of this is 2 because we started with a 4 and I divided out twice. That's why it goes down to a 2. It is not a 3. So you could use quadratic formula, but this one's super easy to actually solve because I could just subtract 4 from both sides because there's no x term. Take the square root. X equals plus or minus 2i. So these would not appear as intercepts on the graph, but they are certainly zeros. If I plug in 2i or negative 2i, they give me 0. So now I have all 4 roots. 3, negative 3, 2i, and negative 2i. So now if I want to write this as a factorization, I can just write each of these as x minus its root. So x minus 3, x minus negative 3 is x plus 3, x minus 2i, x plus 2i. So again, we kind of use technology to obviously aid our work, but to find these complex and irrational, you have to do this synthetic division. You have to be able to use the quadratic formula. All right, that is all for section 5. If you have questions, please let us know.